Hey everyone, good morning, good afternoon, good evening. We'll get started in a couple minutes here. All right, why don't we get started? Hello everyone, welcome to this G-PST webinar on emerging global practices for inertia needs assessment and real-time monitoring. My name is Gord Stephen. I'm a researcher at the National Renewable Energy Lab and also a co-lead of G-PST's Pillar 2 on open tools and data. And I'll be moderating today's session. If you're not already familiar with G-PST, this is an expert and practitioner-driven initiative engaging key power system operators, research and educational institutions, governments, businesses, and stakeholders in all regions of the world to accelerate clean energy transitions at ambitious scope and scale. The G-PST Consortium provides coordinated, holistic, end-to-end support and knowledge infusion for system operators pursuing clean energy transitions, including performing cutting-edge research, providing implementation support for world-class engineering and operational solutions, supporting workforce development, building and disseminating open data and tools, and accelerating localized technology adoption, standards development, and testing programs. We have two great speakers today, followed by a joint Q&A with both of them. Before we get into that, I'll just go over a couple quick housekeeping items about the webinar. First off, this meeting is being recorded and will be available later to folks who have registered. You'll be automatically muted throughout the webinar, but you can engage in the conversation and participate either through the chat feature in Zoom or the Q&A function, which is where we'll be collecting questions for the Q&A session after both presenters have spoken. If you have technical issues, our resident Zoom whisperer, Sophie Schrader, is on the call, and feel free to use the chat feature to message her if you're having any issues. You can also adjust your audio through the audio settings. If you're having audio problems, you probably can't hear me say this, but hopefully you can see this on the screen. There's also a phone-in option if you're having internet problems, and the information on that's available in your registration email. And finally, at the end of the event, after you leave, you should have a survey pop up. We would really appreciate it if you took a moment to fill that in. That feedback and information is really useful to us to help guide future webinars and target where we should be focusing. Okay, so with that, I will stop sharing and introduce our first speaker for today. That is Lina Ramirez. There we go. Lina is a researcher in NREL's Grid Planning and Analysis Center, where she also leads G-PST's Pillar 2 on system operator technical support. She has more than 15 years of experience in power system operations and planning. Her research areas include power system operations and planning, frequency stability, flexibility, resilience, power system markets, system strength, technical requirements for grid forming and grid following inverters, operating reserves, and the control center of the future. Today, she'll be providing an overview of the challenges and emerging solutions around inertia management. So thank you, Lina, so much for being here, and take it away.
Good morning, good afternoon, good evening. Thank you, Cor, for the presentation. So yeah, today, as Cor was mentioning, we will be talking about operation and planning frequency analysis during the rest period. So all the challenges that we have with the reduction of inertia when we start to have more renewables and IBRs in our systems. So just to start, I want to, one second. Okay, so let's start talking about the evolution of the power system and how we start to see that evolution in the frequency response during the resting period. So in the past, as we know, the systems were driven with synchronous generation, so almost all the resources were synchronous, and at that point, the resources that we're providing, like the first response after an event, was that kinetic energy, so providing that energy, responding really fast. So let's say that one generator trip, and immediately all those synchronous generators start to provide that kinetic energy, and they avoid to have like a lower nadir and continue the system working after the largest contingency. Now we start to have more synchronous, more IBRs, less synchronous generators. We start to include other devices in the systems as synchronous condensers. Also, we start to use load to provide that kind of services to provide that frequency response during the resting period. So now we start to talk about critical inertia. So where is the minimal inertia that we need to maintain in our systems, that after that largest contingencies, we don't have like any load tripping. And also, as we start to have more IBRs, we start to include other services from IBRs, so that we start to include fast frequency response that can help to reduce that critical inertia. So that is currently the things that are happening. In future, we are expecting 100% renewable systems. That means that we will have grid forming, grid following, and also synchronous condensers, clean synchronous generators, less than in the past that all the system was driven by synchronous generators. And we also are including load to provide that kind of services during the frequency response during the resting period. So in future, when we have a lot of IBRs, we start to think that talking about critical inertia will be not the best way. And at that point, we need to start to think more about near instantaneous frequency response that can be provided by synchronous and non-synchronous devices, and that amount of energy that should be provided after an event. We need to consider that in the planning and operation in order to have enough resources that can provide that energy in the system, that responds in the system after the largest contingencies, and avoid tripping load. So we will be talking during these presentations regarding the issues that we try to solve and the possible solutions that we are also seeing to solve those issues. So let's start with the motivation, or what is the biggest concerns that we have, and what is the main concern for system operators about frequency stability after an event. So we have here one example of one event in National Grid ESO. So we start to see what happened after they lost 1,400 megawatts. And so at that point, they had one nadir that was 49.1 hertz, and the resting period was 23 seconds. So at that point, they were safe, so any load tripping, and that is like the concern of system operators. How to maintain that frequency stable after that largest contingency, that they are not tripping load and maintaining lights on during that period. And after that, they will have other resources that can provide that response and continue helping to maintain the frequency in the stable number. Could be 50 or 60 hertz. But later, for example, in this example that we have here, they had another event near to the first one. They lost other 200 megawatts, and they had an nadir that was below the under frequency relay, and they start to disconnect load. So that is the main concern. So to avoid to disconnect load after an event, to avoid to have like a biggest event, that is the main concern. So to have the resources that the system needs to avoid that the nadir is going to that point when we start to trip load for maintaining the frequency stable. Also, it's not only regarding nadir. So as we know, we need to consider also a critical work curve, because in some systems we have protections or some generators that could trip if we have like a critical work curve in the system. So there is other main point that system operators are considering. So to maintain that work curve in a safe level during the largest contingency to avoid tripping generation or load that can also create a biggest event. Also regarding frequency during the resting period, so we need to consider that in some systems, the frequency is not the same in all the points. And it is because it's not the same issues in every area. So we can have a really low system strength in some areas that can change the amount of response of the system and can change the recovery and the nadir. So we have here an example in the left where a real system where we have different frequencies in every point that is taking account the measurements of PMU. So there is one important point that we cannot consider that the frequency is the same in all the points. It will be different, and that could be also very different in systems that are not well interconnected, or in systems where we start to have a lot of IBRs in some areas and start to decrease the system strength. So there is one important point that we are considering. And also that means that we can have a different recovery. To the right, we can see an example how we can have different recovery for the same event. And also it depends where is the event located, the size of the event, and how is that even related to the generation that we have connected at that specific point, and the inertia and the system strength that we have in the system at that specific point. So we are considering that is an issue, so that frequency is not the same for all the systems, recovery is not the same, and we can start to consider that maybe in some areas, if we are not considering that critical recovery, and we consider only one global recovery, we can start to trip load or generation. Also, another issue is that, as I mentioned in the beginning, the critical inertia or inertia floor. So having that critical inertia is important now when we have synchronous generation and IBRs, but in future that we are expecting to have more IBRs. Maintaining like that critical inertia floor means to curtail renewables, and that is one thing that we want to avoid. So currently systems are looking to decrease that critical inertia. They are including new services, new devices, as we can see in National Grid, in NAIMO. So where they, in Air Grid, where they start to include synchronous condensers or grid forming, that they can have response from other devices in order to avoid curtailing renewables, because they have like a floor of inertia that they need to maintain. So there is another issue that is important now to consider that critical inertia, but as the system starts to evolve and to include more renewables, we need to decrease that critical inertia, and maybe in future, as I mentioned in the beginning, we need to consider to avoid talking about critical inertia and more talking about where is the frequency response that we require during the resting period, and could be synchronous or not synchronous. Other issue that we start to see is that now critical inertia is more something that we develop and study, and in the planning, and we define that target, and we start to consider that threshold in the real time. So we start to monitor inertia and consider that threshold to avoid to be below that critical inertia level. But we start to see that there is not enough. So here we have some examples from ERCOT in some studies that they are developing. So ERCOT system transmission needs for years 2025 to 2029. They start to talk about that maintaining that critical inertia is taking that they need to reduce the amount of renewables that they can include in the system. So there is one concern. So we need to reduce that amount of critical inertia and to solve the stability issues in order to include more renewables. And also from ERCOT, also we can consider that in the long-term system assessment that they are developing, so this is the one that they developed in 2022, they start to mention that they need operational considerations such as maintaining a minimal level of system inertia, and they need to be evaluating that kind of inertia or services, ensuring reliability under high renewable penetration conditions. So here, like the main point is that for planning studies, we need to include more what is the amount of resources that we need during the resting period, what type of resources, in what time they need to respond. So that is important, not only developing one study, defining critical inertia, is also how to define in the planning studies the resources that we need to maintain the stability of the frequency during the resting period. Also, is really important, so it's not only considering in the planning and defining critical inertia and the amount of reserves that we require during the resting period. So it's also important in the control room to have like awareness of where is the system, where is the system conditions, so what is the inertia now and in future, where is the fast frequency response or the response that we are having, the amount, if is enough, also to see if we have a good work-off, a good nadir, considering that we start to have like some metrics and also some studies that can show in control room if the system is in a secure level, if they have the largest contingency. So this is also something that we need to consider for inertia estimation in G-PST. So we are consider 3 ways to develop that system inertia estimation. So unit commitment, we develop a tool that Eskom is using, and we will be talking about later in this presentation about that. And also we start to think that maybe that is not enough, and I will share later why not. So we start to consider other ways to estimate inertia, so continuous signal and even driving are the options that we start to consider. And to see what is the trade-off and what is the best method to estimate inertia online and how they can complement. So regarding the solutions, so we start to see here that frequency during the frequency stability during the resting period, as I mentioned, is not only talking about where is the critical inertia. So we need to start to consider other metrics that can help us understand if the system is in a secure level and if after that largest contingency, the system will be fine. And also to considering the planning where the resources that we need to maintaining that frequency is stable during the resting period. So here we start to think that we need the following metrics. So considering nadir zenith, so during planning studies and also during real-time work-off, as we know, so it's really important to maintain a secure work-off in the system to avoid tripping of load and generations. Also inertia, so as we have synchronous generators, so where is the inertia in the system? Arresting time, so that is really important. So where is the time that we are having that nadir? Because in that time is the time that we need to deliver that kind of response, that fast response in the system to avoid to having a nadir that is going below the under frequency relates. And also to start to track the new services, so instantaneous frequency response, so that the system operator can see, and also in the planning studies, we can see where is the amount that we need, where is the amount that we have, and if is that enough or not. And also for planning the resources that can provide that kind of response. Also, we are thinking that maybe other metrics could be helping damping. For example, it's difficult to talk about damping during the resting period because it's really short period, but maybe to extend a little bit more and consider more seconds after the nadir and start to check damping, because we start to see that also oscillation is something that we need to consider for frequency stability. Also, as we know, system strength, so that is really related. So inertia and system strength are linked, and maybe we need to start to consider other metrics, but until now, we see that critical inertia is not enough. So including nadir, zenith, work-off, arresting time, and also instantaneous frequency response are really key. We will be talking about every metric that we are thinking that is important. So, and with also with examples of system operators that are including that. So here we have how in the left figure, we see how EarthGrid is including like some forecasting and some simulations for predicting nadir and zenith during the real time. So they start to consider that not only critical inertia is enough, so they are running some simulations during real time to predict with the amount that they will have of renewables and the dispatch that they will have in the next minutes, how will be that nadir and zenith in the system, if they are in a secure level or not, taking account the largest contingency. Also to the right, we can see how the system operator in Colombia XM is developing some flexibility studies, and they are considering in the planning studies, in the resource adequacy studies, how the nadir is evolving, and if for those dispatches in the following years, they are having a nadir that is below the threshold after having the largest contingency. And we can see here that below 59.4, that is the trigger of the under frequency load shedding. So they start to have some periods of that future scenario where they are tripping load. So they need to consider new resources or new devices to avoid having those events in the system. Or it could mean, if they are not defining new services, new devices, could mean that they need to curtail renewables for those periods in order to maintain the nadir in a secure level. Regarding ROCOV, so also EarthGrid is tracking ROCOV in real time. So it's the same, they are running simulations. And here we see also how the system operator in Colombia is including ROCOV studies from the resource adequacy. So for the next 2 years, in the flexibility studies, they start to consider how will be the ROCOV, if the ROCOV is in a safe level or not for the following dispatch that they are expecting in the next years. Regarding, as we mentioned, so maintaining that critical inertia or that inertia floors could mean that we have some curtailment of renewables. So we need to consider, well, if we want to include more renewables in the system, if that will be the best solutions, or if we need to think about other solutions, as EarthGrid is considering that they are starting to include more synchronous condensers to reduce that critical inertia floor. And that means that they will require less synchronous units in the system operation. And that means that they can include more renewables and avoid curtailment. So they are going to studies and they are analyzing, like in the planning studies, where the resources that they need, where is the type of response that they need, and they are defining those and they are commissioning those in order that in future they can reduce that critical inertia level and also include more renewables in the system. Also, other metrics that we mentioned is the resting time. So time to reach the nadir. So that is really important. We need to analyze that really well in planning in all the studies, and also with all the historical data, because that can help us define the resources and the time of delivering that response in the system. So tracking that resting time period during real events, and also with the studies, planning studies, we can define where is the type of response that we need to have during the resting period in order to have a frequency stable and avoiding tripping load. Also, other important point is having reserves. So as we mentioned, in the future, as we will have more IBRs, so talking about only inertia is not enough. So we require other services that can provide near instantaneous frequency response. So here we have in the left an example from IMO, where they are considering like grid forming and new technologies to provide that kind of service. And we can see how that service is really fast. So grid forming is helping them to maintain the frequency stable, to avoid a tripping load and having a nadir below the threshold. So there is one solution that they are identifying. Also, the same thing they are doing for synchronous condensers. So they are like having that kind of service, but is like open to any technology that can provide the service. At the end, I think that there is a best practice to define a service and all the resources that can provide that service. They can participate if it's a market or a technical requirement. So, and for that, for defining that new frequency requirement, is important to define with the studies the magnitude of the response. So where is the amount of reserves that we require for the system, the speed of the response. And we are talking here is near instantaneous frequency response. They should be really fast. And the delay of the response at the dead band that we need to consider for that. To the right, we also see from XM, the system operator in Colombia, how the inertia and the frequency speed response is related. And that is really important because having like resources that can provide really fast response can mean that we can decrease that critical inertia levels and include more renewables in the system. Now talking about online inertia estimation methods. So as I mentioned in the beginning, so in G-PST, we are considering new ways to tracking inertia in real time. So currently we have an open source tool that is using the unit commitment. So we are tracking the age of all the synchronous generators that are in the system and also providing a display in the control room for that. Eskom is using that unit commitment approach. And also we are studying and trying to consider new ways to provide that online inertia estimations as using continuous signal, real-time estimation of the known stimulation, or also consider natural small perturbations, and also considering event-driven ways to estimate online inertia. So here we can see that every method has some pros and some cons, and we start to see that having a combination of them in the control room will help to define like in a better way, like the inertia in the system. So for unit commitment, we see that it's really easy to implement, but we have some trade-offs, like for example, we cannot track demand side of, so considering inertia or also IBRs for that approach. Having like real-time estimation of the known stimulation. So the pros of that is that we can track and also fast frequency response inertia, and it will be real continuous inertia monitoring. But for that, maybe we can introduce some unwanted disturbance to the system operator because we will be providing some signals to the system, and we need to also additional hardware deployment, so it will be a little bit more complex to implement. Regarding natural small perturbations, so the good thing is that we can also track demand side inertia and fast frequency response, so considering the response that IBR can provide during the resting period. And it's also real-time continuous inertia monitoring, but we can have some trade-offs regarding the relationship between the power imbalance and the frequency variations that cannot be captured as we don't have like, where is that small perturbation, and tracking that relationship between the imbalance and the frequency variation. Other approach as event-driven are helping to understand if the other methods are working well. So for that, it's not in continuous inertia monitoring. So it is only when we have events in the system, we can track demand side inertia and also inertia from IBRs. But the problem is that it's only under event. So it's not continuous tracking inertia. It's only when we have an event in the system. So in summary, so the work that we are developing in G-PST regarding how to consider that response that we need in the system during the resting period to provide, like after the largest contingency, to avoid tripping load. So we're thinking in a framework where we need to consider that response in all the stage in the operation and planning. So we are talking here that we need to track the metrics that we mentioned at the beginning, so the nadir, zenith, drop off, inertia, resting time period, and instantaneous frequency response in the historical data, so in the past, to see in the past year, in the past 2 years, how those metrics perform. Also, models are really important as we will be developing studies and we are developing studies. Model validation is key if we can see similar results in real time and in the studies. And for example, EarthGrid is doing a great job in that, tracking like nadir, zenith, drop, and they are studying if the real events are matching with the models. So that is key, because at the end, if we will define with the studies the amount of reserves that we need to have good models for defining that kind of reserves. So also real-time monitoring, as we are doing, so tracking inertia and the others metrics is really important, and it can provide awareness to the operator to see if the system is in a stable way after having the largest contingency, and if they have enough resources to provide during the resting time in order to maintain like the lights on. Forecasting like those metrics is important, so having some simulations or some analytic techniques to forecasting the metrics is key, and doing analysis, RMS, EMT analysis to check if we have enough resources for providing that frequency response during the resting period, considering also in the unit community production cost and resource adequacy and capacity expansion studies, in order that in future we have the resources that we need to maintain that frequency stability during the resting period. So in summary, so inertia may not be the only metric needed in the energy transition to keep the lights on after a biggest contingency of the system. And what is really necessary to keep frequency stable and the lights on after an event is to plan, operate, and monitor the evolution of the frequency, and use new technologies or mechanisms to provide the mitigation required for each system. So thank you very much.
Thank you, Lena. That was a great overview, covering lots of different parts of the world, from Europe to US to Australia. Now we're going to go to a different part of the world as well, with our second speaker. So Bongs, if you want to start sharing your screen. Bonginkosi Sibeko serves as chief engineer at the South African system operator Eskom. Over the past 20 years, he's worked in power system network planning, real-time risk analysis, supply quality, information flow of recent power system events, optimization of the transmission network, support of short-term market tools, dynamic studies, frequency and voltage control operations, planning, outage, and outage scheduling. So Bongs is going to give us a bit of a deeper dive into Eskom's particular experiences around inertia monitoring and management, and their experiences working with that G-PST tool that Lena alluded to earlier. So Bongs, over to you.
Thank you. Can I confirm if you can see my screen?
Yes, looks good.
Okay. Good evening and good morning, everyone. My name is Bonginkosi Sibeko. I'm just gonna share our experiences in Eskom on how we, in the past, managed to monitor the Inertia, and then what we're doing currently, and then what we intend doing in the future. So we're developing a real-time Inertia monitoring tool in a sparse isolated network. This is our team, and the content, the background. I also share what we did with offline inertia estimation using multivariate analysis. What we currently do with the real-time inertia monitoring tool, and then the working process. So just the geographical layout of the SAP network, South African Power Pool. So that comprises with most of the countries in the southern region of Africa. So we have 3 control areas, mainly the Eskom is the biggest in those. Then we have ZISA in Zimbabwe and also in Zambia. So just estimate from Cape Town in the tip to around Zambia, it's about 4,000 kilometers of line lengths. Then we are all connected. Some lines or some interconnections are very weak, But when we are connected, Eskom controls the frequency. We have other countries that will soon join also the SEP. We're talking Tanzania and Kenya. So you can see how the sparsity of the network will be in the future. So the brief history of Eskom and how we managed the low levels of inertia. So Eskom was founded in 1923, and it was called the Electric Supply Commission. And then in around 1930, there was a boom in the gold fields, and the rise of gold boosted electricity demand. Around 1970s to 1995, we installed the first nuclear power station in Africa. So comprises with two units, about 1,000 MVA each. Then we built more gas-fired turbines, coal-fired, and also pump storage stations. Around 1995 to 2010, there was an electrification on a massive scale. That was also due to low prices of electricity, also to stimulate growth. I think by then we were the first or second cheapest electricity provider in the whole world. Then in 2001, Eskom won the Global Power Company Award. Current challenges from 2018 to 2024, we're seeing increase in renewable energy. We're seeing the general underperformance of the of old generators, especially coal power stations. We also see the poor instantaneous reserve and regulating reserve services. We're experiencing load shedding where due to shortage of generation, we switch off customers maybe in every 2 hours or 3 hours. And also we decommissioning some of the old synchronous coal plants. So during those times, how we adapted to different levels of inertia. So around 1930s, we had smaller sized units. Then also the material that they used were heavier, like we're using iron steel, compared to how the recent power stations, what they used recently. So these steels were heavier, and then they could store in a lot of energy. Then because of their small size, any disturbance we didn't affect much the entire entire system. Then around 1970s, 1995, we had medium large size generators. So we're talking about around 300 to 500 megawatts of generators. Those generators comprise what we call latent energy. So whatever it tripped, the energy was stored and then it was released to the system. We installed a lot of flywheels and then some flex devices. Then generally the performance of the generators was quite good. I think maybe in a year we will maybe have 1 or 2 trips. 1995 to 2018, more coal plants than larger ones, up to 720 now of coal plants. Then we have higher stiffness in the network, so we built more transmission lines, even as high as 765 kV lines. We have good regulating reserves and IR, instantaneous reserves. Then the transmission strengthening was good. We plan on N-2 planning. So that means if we lose if we lose 2 lines or any 2 generators, the system must be intact. Then obviously general operational discipline. Challenges of how we're doing to mitigate the current challenges. We are building more battery energy storage schemes. We are repairing the maintenance of generators and doing a lot of maintenance on generators. We are contracting now instantaneous reserves and regulation reserve to IPPs, to independent power producers, and also to the load side of things, and then of the network. And then we're recovering pretty well from load shedding. I think we went 30 days without shedding in the past few months. Then we are developing the real monitoring tool. It's what we're going to discuss later. So I think that this picture I stole it from initial estimation in modern power system from the K-Babaka. Generally, we have synchronous generators and a high penetration of non-synchronous generators. So the results of the power system, we have low and fluctuating inertia. Then the problems is the frequency stability, higher rock-off, and the blackouts. Luckily in South Africa, we haven't, or in Eskom, we haven't experienced total system blackout ever since Eskom was found out. Then the challenges or the possible solutions is Inertia support from smart load, Inertia forecast, and VI control. What we've done is we've done offline Inertia estimation, and then we depended highly on historical data after last disturbances. What we're currently doing now is to develop an online Inertia monitoring tool. Then in future, we want to predict online what's going to be happening. Just one of the things of preventing the power system or the collapse. So this is just the frequency on the left-hand side. And these are just levels of frequency if we lose units or any generators. So this green side is we find normally we can go up to 4930, but there are things that we do. Unscheduled hydros, we run gas turbines, and then there is auto starts of power pump storages. Then below we have UFLS, under frequency scheme, load shedding scheme. So that kicks in at around 4920. Then thereafter, there's also other under frequency load schemes up until stage 4 of that. So all these are automated. So the last time we triggered this UFLS 4920, it was in 2015. So what happened after 2015, we contracted a lot of IDR, instantaneous demand responses. So at around 4965, around 4950, there are certain loads that automatically gets disconnected for about 10 minutes, then it reconnects again if frequency goes to those levels. The challenge now is having all these automated schemes. What we're currently doing is reviewing, should we initiate or the rate of change be so low, we can trigger all these levels, and then we can go from low frequency to high frequency, of which is dangerous than the low frequency, because there's not so many things that we can do at higher frequency. So offline estimation, what we did in the past, the method that we did, we used the multivariate analysis. This is based on the statistical principle of multivariate statistics, which involves observation analysis of more than one statistical outcome variable at a time. So on the left, it's a real incident. We tripped one of the large units in the north part of South Africa, about 700 megawatts. Then we measured using 3 different measurement points, one in the south, one in the central, and one in the north. So you can see that where the unit tripped, there's what we call subtransient. I think April they call it electromagnetic energy storage. So units that are around the disturbance, they tend to, the internal resistance of those generators tends to be lower, then the current goes higher. So you get a lot of initial response from the units that are around there. But you can see other areas, they didn't see that subtransient. They contributed, but not as much as those in the area. What we did is we realized that, okay, there's a lot of methods of calculating calculating the inertia, but it can be grouped into 2. Inertia method is more or initial constant method is more of the precise method. So you need to know all the generators data. You need to know everything. So your visibility must be good, and then the tie line flows and everything. Then also there's another method of which is a swing equation. So what we did, we used both methods and then correlated the 2 methods. Then then we did regression and analysis, and then we came up with some formulas. So we used Excel for this. It was a manual and tedious process, but obviously if you use regression, R squared must be closer to 1 just to check if the model is good. Then the F must be large, and then also the standard. So there are some ways of checking if the if the method or the correlation is good. So this is, we took about, from 2015 to 2017, we took about 2,000 frequency disturbances. So there's a lot of data that we have, of which even if a day we can have up to about 5 trips. So we have a lot of data available. So this is one example where we took about 30 observations in one area. Then we took different variables. Stiffness was one of them, and then also we added all the units that were synchronous on load during the disturbances, like the MVAs or maybe the J's. Then we took at that time we take the spinning reserves, and then we take also what we call the load losses or partials, units that are not doing that are not capable of doing full load. Then we took the tie lines or the tie line flows to estimate how much of the neighboring countries, how much of their units are synchronized. Then also we added wind and PV. So it's just variables that during the disturbance, what was happening during that time. Then we managed to come up with the formulas. This one is the Inertia with the FPR, which is the first primary response. Then we can check, or we can check using the formula. We can check the frequency that of that. Then the other one is Inertia without FPR. So the first 300 milliseconds or half a second, then we can see how much rock-off or how much Inertia is in the system. What we did from those formulas, we took newer events in 2018. Then we tried to test the model. So from 355 actual disturbances, 225 disturbances resulted in errors with less than 5%. So these are just power stations and then events that happened. For instance, Hendrina had 5 incidences, and then these are the prediction error of margins. Then about 8 disturbance caused errors greater than 10%. So the model was tested for that. And key contribution of the work, we identified the weak areas in Eskom network. Disturbance size and measurement points is crucial for the model accuracy. System stiffness significantly impacts the model accuracy. Initial constant assumption invalid for sparse isolated network. So you cannot just take all the units across the network of the sparse network and then add them and say you've got an initial constant model. So it's only applicable to a meshed network and smaller in size. Relevant variables are identified and weighted. So we could see whenever we have high wind, then we take off some units, what is the impact of that? Whenever we have certain lines that are out in the system, what's the impact of that? Whenever the stiffness is low, like the damping is low, or the damping is low, and the governance for the second method, if it's low as well, then we can see that the stiffness plays a big role. The other one, model uses analytics with data from Eskom. So if you have a lot of data, you can develop something like that, and then using analytics. Model can be integrated into other open source tools, and then we successfully predicted the rock-off and frequency nadir using the model. So what we're doing currently with developing the real-time Inertia, so in collaboration with NREL, we had a generic model which is written in Go and available online to get feel free to test the network. Then we customized the Inertia monitoring tool for Eskom network. This is what we're currently doing. We are adding some variables, and then it's live. We can track the Inertia of the system, but the basic level, we're still gonna make it more complex by adding stiffness and other variables that are needed. Then the system interfacing, interrogation, and debugging. So obviously from the studies, we know how to filter out some events that causes errors. So some units like PDC can cause errors, and then small disturbances can cause errors, and then the units or the incidences where IDR or instantaneous demand response operated, we need to filter out that. So those are the things that we're gonna do. We're gonna put on the initial material 2. So this is an example of the display that we can see. So obviously you put the username as a password, you clean the data, perform relevant checks for unique breaker status, then other things. You do your initial calculations and then update. For now, we can set it whether 60 seconds, even 10 seconds. You can just choose it, the model. So this is just a screen showing, okay, maybe if there's a critical level of inertia, and then what is it in real time. So work in progress from the PMUs or from the WEMs, we need to have area frequency. So frequencies are not the same. Whenever there's a disturbance, frequency will never be the same on the system for a shorter period of time. Then we get damping from PMUs. Then we can also get a rocker from PMUs. Then from the energy management systems, we can get the synchronous generators. We have the MVAs, we have the rotational mass of the system. We have the breaker status, and then whether units are in AC or synchronous condenser mode. We know spinning reserve per area. Then we know generation schedules. We can also have partials or load losses, system frequency, stiffness, fault levels, IPPs, and tie lines, and some alarms. So these are the work in progress that we're incorporating the new tool that we're having. And thank you very much. That's the end of my presentation.
Thank you, Bongs. That was great. So we have about a little less than 10 minutes to go over some questions. We do have a few questions in the Q&A box. If you have a question and you haven't dropped it in there yet, feel free to do that, and we'll get to it if we have time. The first question, it was related to Lena's presentation around near instantaneous frequency response. And why do we want near instantaneous frequency response? Wouldn't that be too fast in terms of resource coordination and cause control problems? So Lena or Bongs, if you have thoughts on that one.
Yeah, good question. So here is first, why is important? So as we know, the resting time period is really fast. So we are considering that some seconds, milliseconds, that they need to provide really fast response. There are resources that we provide that kind of response to maintain the frequency in a level where it's secure, we are not tripping load. So that is the reason, because the event is fast and we need to respond fast. In the past, it was so really easy because synchronous generators were providing that reserve, and it was like the technology in itself, it was providing that. So it was easy. Now we need to consider other resources that can provide that kind of response, really fast response. And as we mentioned, so it's really important to understand during the planning studies if that response is enough for the system, what type of resources we need in order to avoid other problems. So in the studies that we are developing, we start to see for sure control problems if we have really fast response, that we don't have like good tune of the resources that are providing the reserves. So for that reason, we need to consider other technologies as grid forming, that they are included, also damping, and other solutions that could be complemented in the first time where we have an event, so in the resting period specifically. So this is an important point, that we are concentrated in that particular time where we need like a fast response in order to avoid tripping load.
Okay. Another question, sort of in line with the end of that last one. Do we need inertia that like we've traditionally had, or do we need something else, maybe something more nuanced? And then the question makes the point that inertia going into an event is a good thing to arrest the frequency change. But obviously when you're recovering, you maybe want to not be as slow necessarily. And with things like IBRs, there's the ability to be, more adaptive or dynamic in what the response is at different points across the event. Do either of you have thoughts on that?
Okay, going to that question, so good questions. Yes, we need other type of response. It's not only inertia, because if we talk about inertia, it's only synchronous generators. So as we presented, if we say that we only can manage the system with synchronous generators, so that means curtailment of renewables, and we cannot have like a 100% system, renewable system. However, in future, we also will have some synchronous response from synchronous condensers, also for clean synchronous generators. So that will be a combination between IBRs and also synchronous devices, and load is important too, that can provide that service. And also those resources and the amount of response that we need and how fast we need to understand really well that with planning studies, with good models, that we can be sure that in future we have those resources that are additional to synchronous machines that can provide the response that we need during the resting period.
Maybe related to that, another question: can synthetic inertia be a complete replacement for traditional inertia, or are there other services missing? The points made about potential like economic trade-offs with IBRs and short circuit current and needing to oversize inverters to have enough fault current. But are there reasons that you couldn't fully replace synchronous inertia or synchronous machine, traditional inertia with frequency control from IBRs?
So here is a really good question. We didn't have the time to talk more about that, but we start to see that every system is different, and system needs are important to consider when we are talking where is the amount of response that we need during the resting period. So as we presented, we can have systems with weak areas and with other problems that are not only inertia, could be also system strength. So we need to understand well where is the system needs and how we can complement the responses of the devices, what devices we need for that kind of system and for that kind of problem, and could be in only one region of the system that we need some type of response. In the other part of the region, we could need another response. So understanding really well where is the system, where are the problems, doing like planning studies to understand really well what is happening, and trying to find those solutions in advance so that we are not dealing with that problem in the control room, that we are solving the problem before going to the control room is key here. And yeah, I think that is more depending of the system. Could be other issues that are not related only to inertia. So could be system strength and also limitations of the resources that you have in the system, maybe slow responses of the synchronous clean energy machines that you have there, or other kind of issues, system constraints that you need to consider, and it's not a single answer for every system.
So like many things, it depends.
It depends, and doing studies is key. So planning studies to understand the issues and the best solutions. And yeah, that is the important part.
Question for Bongs. You have an HVDC intertie within your network model. How do you represent this in your analysis? Is it LCC? I'm not sure what LCC is, but you might. If so, there is risk it might degrade frequency stability rather than support it.
Thank you for the question. Yes, because ACDC, it's non-synchronous. So it's connecting the network in the south to the northern parts, about 1.5 kilometers, and then it's in parallel to the weak AC line in parallel of that network. So obviously, if we are not connected by the AC, the DC line won't contribute at all to the inertia of the system, of the remaining system. In terms of making it worse, yes, in some instances it can make it worse because there are some trigger points to protect the filters in that side of the areas, and then they are rated very lower to other schemes. So HVDC can be a challenge, then it doesn't contribute to the inertia of the system. How it was represented, obviously, it's closer to the 0.00005 compared to other variables. So we just represented it, but it has a 0 inertia compared to other variables, just like wind and PV. I don't know if that answers the question. Thank you.
Thanks. Yeah, and I've just been informed LCC is line commutated converter. So thank you for that as well.
Yes.
Question for Lena. This maybe will be our last one because we're right at the hour or the half hour. In terms in the needs of EMS SCADA application for real-time monitoring, which application is the best for measurement of the impact? Is dynamic stability assessment or EMT simulation needed? And if so, would the EMS not be fast enough?
Good question. So considering some examples from system operators that are dealing with a lot of renewables, so specifically with EarthGrid, so they are doing RMS studies during real time, tracking the rock-up and the nadir of the system, predicting the rock-up and the nadir. Also, as Bon presented, so they are considering other analytics tools to define rock-up and nadir and predicting that. So again, it depends on the system. If RMS simulation is enough for tracking the solutions and tracking the system during the resting time, that is the solution. If we need advanced solutions as EMT, for example, Chile is exploring that, having like EMT studies during real time. So that is also something that is going on. I don't know any system that is doing EMT simulations in real time, but I start to see that some of the system operators are moving in that way to predicting how will be the response of the system after the largest contingency during the resting period. So I think that it depends on the system. Currently, RMS simulations are the ones that are used and analytic like studies, but in future we can see EMT simulation in real time.
Okay, thank you. And with that, I think we're gonna close it. We're over time now. Thank you so much to both of our panelists. Really appreciate you taking the time to share your knowledge and experience on this topic. And hopefully everyone learned a bit. We really appreciate everyone in attendance for being here. Thank you so much. Please do fill out that survey when you leave. We'd love to hear your feedback on how you thought this webinar went. So with that, I think we'll wish everyone a good day, a good morning, good afternoon, good evening, depending on where you are. And we'll see you next time. Thank you. Bye, everyone.
Thank you.
Thank you.